Okay, so yes, so last time we were looking at connectedness, right? Connectedness of what? So we have so far seen connectedness of subsets of R1, right? So we have seen, first of all, why are we even looking at subsets which are connected? So that should be the first question. Why even study these type of subsets, okay, and bother about them? So why connected sets? Yes, have you thought about this? Why should we bother with the kind of sets? Yes, hello, am I audible? Yeah, okay. All right. So so you see, connected sets, why are they important? Or what are we trying to do? So when we are defining connected sets, you can see it like we are trying to model intervals or generalize the notion of intervals. Okay, so you could say that we are trying to define a generalization of the notion of intervals, right? And intervals we know are very important. If you look at all the good theorems in analysis, right, especially at least in R, right, from R to R, you say, then all the good theorems, like for example, the intermediate value theorem, right, that needs your domain to be a connected, that needs your domain to be an interval, right? Otherwise, the intermediate value theorem does not hold. And so, but that doesn't tell you the full picture actually, because a lot of other theorems don't need connectedness. But we will see that when we are doing complex analysis, when we are looking at functions from the complex plane. So when we're looking at functions which are from the complex plane to another complex plane, or whatever you want to say, from complex plane to complex plane, then the domain, right? The domain should be a set which which should be in one piece. Okay. Um, that will be important, especially if you're looking at functions which we want to be good functions, like we have defined differentiable holomorphic functions, right? Then the domain has to be connected, okay, for the good things to happen, meaning there should not be any holes and such, because for some reason we would want to integrate over the set and things like that. So it should be a connect, like even for integration in R, you need your set to be connected. You need it to be an interval. So that's why, and you will see more why connected sets are needed. Okay. So connected sets are certainly important. Okay. They allow us to do the good things that we do in analysis, especially in R2, this is seen. So that's why they're important. And okay, so just to complete this point, what we are trying to do here is to generalize the notion. Okay. So that's why we need a definition. So what we do, so that's why connected sets is fine. But now we look at definition. How do we define it so that we can generalize it, so that we can also make sense of it in places like R2, R3, and so on. Okay, so the definition, as we have already said last time, the definition of connected sets is basically a subset of, now this could be of R, it could be of R2, it could be of any space, but for us, let's say R or R2, okay, is called connected if it cannot be broken up into two pieces, right? Cannot be broken up into two isolated pieces. Okay. Obviously, the word isolated here is important. because obviously you can take any set and you can just partition it, right? You can just set theoretically partition it into two parts. That is obviously always possible, but that is not, that's always true. But what we want to, what the sets we want to look at is those is called connected, sorry, is called connected if it cannot be broken up into two isolated pieces. What we really want to say is that the set should not be made up of two pieces such that all the limit points of one piece or the limits of sequences in one piece are not in the other piece and so on. So they're completely apart from each other. Okay. So we do not want that. Okay. And to put it, right, basically it should not be in two different pieces where in both the different pieces analysis can be done, separately. But to define it clearly and crisply, it will be is called connected if it cannot be written as a union of two disjoint open sets. Right? That was the idea we tried to capture, but then we state it crisply in this way. Is called connected if it cannot be written as union of two disjoint open sets. Now, obviously, open sets, we know what are open sets, right? Sets in which when you are inside the set, you can make a small neighborhood, which is also inside it, right? Yeah. And we had talked about this the last time, how this captures the same thing about, two pieces such that the limit points of one piece is not in the other and so on. Okay. So I think that is okay, right? That was the definition. But then we classified, we did this classification. So, I mean, what is the next question to ask? The next question to ask is what are the connected subsets of R, right? So we said this, that subsets, that connected subsets of R are exactly intervals. Connected subsets of R are exactly the intervals and nothing else. And nothing else. So this is exactly the intervals. This is the first theorem. This is a very important result which we have proved. Now, the next step is to obviously explore connected sets of R2. Right? So the next step is to explore. Now R2 is much more interesting. Connected subsets of R2. Okay, so let's see. Let me give you a few examples and ask you if they are connected or not, and then also we'll try to prove them. Okay, so so remember that we already have the definition of connectedness in R2. Okay, we already have the definition. So okay, so this is, but yes. So once again, open set in R2 will be the same definition. So I'll say it again. So remember that, I mean, you already know this, but I'll just say open sets is not the same as open intervals, right? So first understand that, right? That open set is not the same as open intervals. Open set is again a generalization of the notion of open intervals. Open set just means that if you are inside the set, then you can move a little bit in the set. Okay, so open set, let's define this. So now I'm just going to define it independent of R or R2. Okay, you can just make sense of this. So open set means that, so U in, let's say R2, or let's just stick to R2, U in R2 is open if, and maybe I only defined it for R last time, but yeah, same definition, similar definition will work. Is open if for any point X in U, okay, there is a ball. Okay, there is a ball around X. So we usually call it like this: ball of radius R around X, such that this entire ball, and this is an open ball. Okay, so point X and radius R, open ball, such that this entire ball is inside U. And this happens for every point. Okay, what this is basically saying is that no point is on the boundary. X is not on the edge, right? X is inside, right? So it basically means that the set doesn't have a boundary, basically. Something like this, where it means that wherever you are, if you are here also, you can make a very small neighborhood and still be inside. So it's kind of like an infinite set. It's kind of like this is an unbounded set in some sense. It doesn't really, if you're inside the set, you don't really see any boundary. If you're inside, you can just move a little bit, right? Just the most standard example is this, right? And obviously you understand, you are anywhere inside the circle, you can make a very small ball and still be inside the circle, right? You can always do that. So this kind of sets which do not have a boundary, or I should, to put it more strictly, it is that every point is like an interior point, okay? Doesn't have a boundary, so that's why it's called open, okay? It's like a unbounded set mostly, okay? So the endpoints are like a singularity, they're like, you can't see them. Yeah. So that's what an open set is. Whether in R, this ball will become an interval. In R2, it's a ball. In R3, it becomes a sphere, but we call them all balls. Okay, because same word. Okay, but you see, the idea is the same. Because open intervals are important, right? Because we want to be able to define name. If you're studying some local property like holomorphicity, then you want to be able to define the boundary. Sorry, you want to be able to define a neighborhood around the points. And so the neighborhood, there should be neighborhoods around every point which are inside the set. So that's why we are looking at open sets. And obviously, we also use them to define connectedness. So yeah. So yeah, let's keep this definition here, though we know this, but still let's keep it here. But let's just explore this. Yeah. So really, it is not difficult to predict more sometimes if something is open or not, but it might be difficult to prove. So proving connectedness versus predicting connectedness, they are two very different things. Okay. So if I to give an example, let me give an example. A concrete, yeah. So let's just take a quick example. Let's say that if I draw this, 1 minute. So can I, yeah, let us just take R2. Yeah, let me start with this. Is R2 connected? Well, surely we know that it is, but how do we prove it using these definitions? That is really the point. So is R2 connected? Yes, looks like, right? I mean, it should be that, I mean, your definition should be such that R2 is connected. If my definition is giving that R2 is not connected, then something is very, very strange, right? So it should be, but how do we prove it using the definition? Let's think about that for some time. Sorry, two open intervals. But what does that mean? I don't understand. Yeah. Okay, but they will not be the. Okay, so then what is your point? No, but that's not a proof, right? Is that have I proved anything like that by that? I mean, so maybe what you're trying to say, if you're trying, maybe you're trying to say that since R is connected, R times R is also connected. Something like this you're saying. But yeah, but this needs to be, this is not so trivial to prove, right? I mean, we have not given a proof of this. These kind of statements are good, and the product connectedness is preserved, and certainly they should be. Even more things are preserved, like irreducibility, which we'll define later. But it is not so clear how to prove this. Basically, this is what we're trying to prove. Yeah. In general, you'll see later that if X is connected, Y is connected, it implies X cross Y is connected, depending on how you define the open things in this. Yeah. But what you were, other thing you were saying, and you are right in that, I think that if you take an open set U, then basically around every point you can make something like this, an open rectangle kind of. You can obviously make this. I agree with you. If you can make a ball, you can inside the ball make a rectangle also. But again, this does not prove that R2 is connected or R plus R is connected. Though it can be done by using some projection from R cross R to R, but we want to give a much simpler R proof. Okay. Yeah, so intuitively this is correct, but the proof of this is a little technical, I think. Or if I try to break it down, I have to say a lot more things. So let us try to prove this in a different, easier way, maybe. Just from the definitions. Yeah. Let's try to prove it just from the definitions. And you can see that it can be a little frustrating. So, and that frustration, we will use it to give better definitions of connectedness, more user-friendly definitions. But before that, we should get a little frustrated with not being able to prove such obvious looking statements. Like the epsilon delta definition, it usually is not very useful to at least find limits or things like that. We have to use other criteria. So obviously, if we want to give a proof by first principles, a first principles proof should go by contradiction, because if you look at the definition of connectedness, right, we have to assume it's disconnected so that we have something to start with, right? So a first principles proof should go via contradiction. Okay. So let's write it clearly. Let's use a different color. So assume that R2 is, not connected. What does this mean? It means that R2 can be broken up into two open sets, U1 union U2, obviously non-empty and disjoint, right? So U1, U2, they are non-empty, obviously. I mean, if you make one of them empty, then just take R2 itself as one thing. Okay. See, R2 itself is open in R2, obviously. That's okay. And obviously, the other thing is the U1 intersection U2 is disjoint, is empty. This is obviously important, right? We want it to be disjoint. Otherwise, you can just again write anything. And we want to show that this is a contradiction. We want to get a contradiction somehow. And somehow this even looks incorrect, even if you look at it by this definition of connectedness, right? It looks incorrect, right? That you can somehow break R2 into two pieces. How can you break it into two pieces? It doesn't really look correct, right? But how do we prove it? So that, the proof is logically tuned with the definitions. So let us see. This may be the first time doing this, but this is what we usually do when we assume this kind of statement. And we did a little bit of this in R also. Yeah, maybe something like that, but how? That might work, but yeah, if you assume one of them is open, you show the other is not open. But again, showing something is not open is again, I don't know how to do it. You have to again assume it's open and then get some different kind of contradiction, right? Because you cannot show something is not open directly, right? So let us use the non-emptiness. Okay. See, R2 is connected, that is true, but it's in fact much more than that. Okay. And that's what we will prove. So proving the harder thing will be easier because the harder thing is more concrete. We will see that. So let us say that R2 is a union of two things, right? So then, yeah. That's right. Yes. Yes, it looks. So maybe you're trying to say that you take something on the boundary, but we have not defined these things. That is the problem. You take something on the boundary of U1 and you then show. So you have the boundary of U1 and let's say that something is there. And then you show that this point, which is on the boundary of U1 is not in U1 and it is also not in U2. Maybe that's what you're trying to say. That's something. Yes, I mean U1, U2 are disjoint, but all points on the boundary of U1 that cannot be in U2. Something like that, yeah. But then the point is we have not defined what boundary of a set means. But it looks correct that if we take something on the boundary, then this point on the boundary of U1 is not in U1 because this is an open set. So if you boundary means it's on the edge, you may take any interval, it'll go outside. But then we want to show that this boundary, this point which is on the boundary of U1. So let's say this whole thing is U1 and this other thing is U2. This thing that on the boundary of U1 is not in U2 also. But how do we show that? I mean, no. I mean, first of all, why do we think that it is not on the boundary of, sorry, why do we think that it is not in U2? Because it looks like that, right? But we can't do this because we don't know what the definition of boundary is. Yes, but the point is that there are infinitely many different possibilities of how an open set could look like, right? That is really the problem. I mean, it's an open set, right? We can't visualize it. I mean, you can use the visualization to do some arguments, but yeah, that is the problem. So that's why we have to look for a different proof. I mean, this can be done using boundaries and such. This was easy in the case of R because the boundary was just the supremum of the set. Okay, we could capture it, but here the boundary, we don't know how to describe the boundary, right? And it's not easy to describe the boundary. Okay, so that's why let's leave this approach. In fact, something more easier is there's something more concrete. Yeah, so see, connectedness is not a very concrete property. Connectedness can be abstract. Connectedness can be abstract. We will see this when we study connectedness of rationals. Okay, it's not a very concrete property, but something else is more concrete, and it is more special, but then it's more easier to prove also, even though it is a more specific thing or a more rare thing. But let's see what that is. Okay? So basically, see, if something is a union of two open sets, so let's say this is the two open sets, or maybe, I mean, we cannot really draw it because it doesn't exist, but let's say like this, and you break it. Then my point is that you will find one point in the first open set P, and you will find another point in the second open set Q, because they are both non-empty. That is in the definition, right? So P is in U1 and Q is in U2. Okay. So this is U1, this is U2. Now, because you are in R2, you can make a line from P to Q. That's right. Yeah. Because we are in R2, we can simply make a line. And this using lines and simple objects like lines and such to study complicated things is really the key. Just because we all know what, but we said that we are not able to say it if we don't use lines and simpler things like this. Okay? So it's just mostly a definitional thing game. We have a line from P to Q. I mean, this is obviously a simple line. Now what? Now this problem becomes more like what we already had in R, right? Because what you can now do is you can just take U1 intersection, the line is getting cut right into two pieces, intersection L. So L is a line. L is the line. We don't need equations and such here because we don't have to do any computations. So I'm just saying L is a line joining P and Q. So my point is that this is something much more simpler to do, and we only need this much, and it's concrete also. So U1 intersection L, and then you take U2 intersection L, right? What does this do? This splits the line, right? This part, basically we're looking at the part of the line which is in U2, and then we are looking at the part of the line which is in U1, and this splits the line. And obviously these two are both open, right? They are both open in the line because that they are by definition, right? So we have kind of taken two open sets and broken up the line into two open sets. But that is not possible because we know that lines are connected. Right? Lines are connected is just the same proof as R is connected, or intervals are connected. A line is just like an interval. But again, this is not rigorous. I'll make it more rigorous, but just one step at a time, right? So we wanted to say lots of things, and we were finding many ways to say something, But this is a precise way, and it's actually much more little than arguing about the boundary and such. A simple abstraction. Okay. So in some sense, basically, we have found a disconnection of the line, which is not possible. But once again, this is not formal thing, right? To make it more, we will use continuous functions. So let's do that one step. And this we need, otherwise we will not be able to write proofs of connectedness of other sets and make other theorems, and sometimes this will be necessary even to know the answer because it will not be obvious. R2 is obvious, I mean, but you'll meet connected sets where it will not be very obvious. So that's why so how can we make this more precise? Well, this is very simple. If you take the L, you can write L not as just a static set, but you can write L as a function. Or rather, I should say, you can define a function f from this 0, 1, which is connected to the line, right? You can always do that, right? Because you can just take a line. I mean, yeah, so you can just take a line like this, lambda p plus 1 minus lambda q, right? This function, you can take this as f, which starts at q and ends at p. Okay, so do you see that this is the function, right? This will be the function that is taking 0, 1 to L from traveling from q to p. Because you can see when lambda is 0, image is q. As lambda increases, images. Okay, obviously these are pair of points. So if you want to be very precise, this is saying f of x comma y. You have to give some coordinates. So, but you understand, right? Okay. So basically f of lambda is this. Okay. So is this okay? Okay. This is just the function. Now you see, if this is okay, then see f is continuous. F is continuous. Now what do I mean by f is continuous? You can just say f is made up of two functions which are continuous, right? There are two functions. If you break this coordinates, you'll get two functions. So f is continuous. Now, image of a connected set under a continuous function is connected, right? So f of 0, 1 is connected. Now, again, we have not formally shown this, but now we have full incentive to show this, because we think this should be true and now we need it. Why? Because see, we have shown that L is disconnected. This is basically saying, so let's come back, L, the line. We have shown that the line is, so we wanted to show that R2 is connected. We assumed it is disconnected, but that assumption is not very useful maybe. But from there, we are getting something much more specific, that L is disconnected, because we have broken up L into two disjoint open pieces, right? L is disconnected. But we know in our hearts and minds that a line is not disconnected. And that should be much more simpler to prove. So to prove that a line is disconnected, I am using the fact that the intervals which we have proved formally are connected, and giving a continuous function. Okay, continuous function to L. Now the image is L. That should also be connected, but we have shown it's disconnected. That's a contradiction. Okay, but it is still left to show that image of a connected set is always connected under a continuous function. We have not formally shown this. So that's our next theorem that we have to show. Okay. So this basically says that this is the next theorem that we should show. And that's the number one thing. And the second thing is that if you think about it, we have shown more than just the fact that R2 is connected. We have shown that between any 2 points, and I mean, okay, that's, everybody knows that, right? Between any 2 points of R2, there is a line. But we have shown that, and this I will abstract out. What we have shown is that if you have a set S such that between any 2 points, you can make a line, then that set has to be connected. And this will be important. Okay, so I'm abstracting something. Okay, what we have used in the proof is that what we have only used in the proof is that between any two, we have not used the fact that we are working with R2. This could have been any set S. As long as we had the property that between any 2 points of S, you can draw a line, and connect convex sets are general examples, right? Many strange sets are there. If between any 2 points of the set, you can draw a line, which is inside the set, then that set will be connected. That's another thing that we have proved. So let's take these two things and abstract them out. Okay. So here is what we need to do. So number one, which we need to do, so is this. If f equal to f1 comma f2 is a continuous function. Basically, I'm just trying to say that f1 and f2 are both continuous. For a function from R to R2. So as you can understand, I'm trying to say that f of x comma y is two pieces. This piece, and they have all obviously seen this in complex numbers. They're all like this, right? Functions from, okay, that's C to C, but yeah, like this. If you have this kind of function, then image of connected sets is connected. And that basically means image of intervals. And this is a generalization of intermediate value theorem. Image of, this should be true, but we'll have to prove this. Image of intervals is connected. Okay, this is to be shown. So this is another reason why continuous functions are so good, because if you take a continuous function and you take a connected set, then its image will also be connected. Okay, image of open set is not open, image of closed set is not closed, but the image of connected set is connected. That's why connected sets are better, are nice in that sense. We will show this the next time. This is a slightly formal result, not difficult, but intuitively show this the next time. But right now, to continue with the theme of connectivity, this is what we have shown. If more or less we have shown this, if you assume one, number one, and if you think about the proof we just did, if S is in R2, okay, such that between any two, okay, let me say it like this. If R2 such that if x comma y are in S, any x comma y are in S, then, or maybe I'll say p comma q. If any p comma q are in S, then there is a line, but now I'll say a more general statement, then there is a continuous function such that there is a continuous function f from 0 comma 1 to the set S, such that the continuous function is like a curve, parameterized curve, which we talked about in the real analysis class, f that starts at one of the points and ends, roughly speaking, I'm saying, at the other point. By definition, precisely this is what it is. So what I'm saying is that between any 2 points of the set, you can go from one point to the other using a continuous function. Okay, then S is connected. And you see the exact proof of what we did. Just replace the line by image of a continuous function, and everything else remains the same, right? Replace R2 by S. That's all we have used about R2. We don't know anything else, right? What else, what more can we use in this context, right? So you see, we only use the fact that, you see, so the point is that we took a simple example like R2 and we learned two theorems, right? That You don't need R2, you just need the fact that between any 2 points there is a line. But then, oh, okay, we don't even need a line. We just need that in place of that line, it could be the image of a continuous function. What example can I give? You could take something like, so yeah, you could take something like this. Right? So what do I mean? I mean that if you take this point and this point, then there is no line between them that is inside the set. By inside the set, I mean inside. So you know that inside is this part. But yeah, then there is no line between these 2 points. Okay, but we don't need a line. There's a continuous function, and the same proof will work. Right? If this was disconnected, then you can break it like this in some way. Then you pick one point and one open set. You pick other point, other open set. You have a continuous function. Then the image gets broken up into 2 pieces, but the image becomes disconnected. But we know that the image of a continuous function is not disconnected, and so on, right? So the same proof works. You don't really need a line, and you may not always have lines available to you. Okay. So is this fine? This is a good result we have proved, which is more specific thing than connectivity. Yeah. Yeah, it's a more specific thing than connectivity. It's what is called path connectivity. But so it's more specific. I mean that this does not, I mean, this implies connectivity, but not all connected sets are like this. Some connected sets are very bizarre. We can't visualize them. They are not like this, but they are still connected. Okay, but this is a special kind of connectivity. Okay. This, so sets, such sets are such, they're obviously connected, that we have already said, we have reasoned it out. You can still write the proof to make it just to see if you don't have any holes in that. But such sets are connected, but such sets are connected because that's what we already said. But such sets are more than connected. More than, just 1 second to close this. Yeah. That was a little different. I mean, yeah, so that was like a weaker condition than convexity. But then under some continuous assumption, it became convex. I will not say that those are very related concretely. Okay. But this is an example of a situation where you have made a definition which is pretty abstract. Connectedness is an abstract definition, union of 2 open sets. So can we see the open sets in R2? No, they're very bizarre open sets. You can't imagine, and there are uncountably many of blah, blah, blah. Okay. But the point is that in nature, when you find connected sets, they are not those bizarre pathological sets. They will be nice connected sets, and they will be of this type. They will be connected, but they will be more than that. Between any 2 points, you can travel by a continuous function. Okay, such sets are more than just connected and are called path connected. Obviously, convex sets are path connected. Convex sets are not maybe formally defined, but convex sets are just sets where you take any 2 points, the entire line will be in this. So this set is not convex. I'm sorry. This is not convex because if you take this point and this point, the line is not inside, but it is still connected. But convex sets are obviously path connected because between any 2 points, there's a line inside the line segment is inside. That's the definition of convex sets. Okay. But any case, so what's the definition of a path connected set? Path connected set is a set where, so don't go by the definition that it should be connected. We have proved that it is connected. Okay, but the definition is that between any 2 points inside the set, there is a path. And by path, we have to be very precise. The definition of path here is, obviously, you will know it by seeing, but to prove it, you have to actually show it by the function, that there is a function that takes this to this in a continuous way, in a nice way. Okay, these sets are called path connected. So remember, connectedness does not imply path connectedness. Under some pathological conditions, connected sets will not imply. I don't know of all the conditions. There might be some nice cases also where connectedness does not imply path connectedness. But under some pathological, 1 minute. Yes, yeah, there are some specific cases, closure and such. Connectedness does not imply path connectedness. So we have to, so I mean, if you really want to show, but what if I'm wrong? I might be wrong. I'm not proved, right? We have proved that path connectedness means connected. That is just the proof we did for R2. Sets of type S. But I'm saying that connectedness is a much more specific, is a much more general thing. There may be sets which are connected, but they are not path connected. There may be, but one needs to give an example. Example is needed here. Example needed. I mean, unless I give an example, I'm not, this statement is not true, that connectedness does not imply path. Okay. So we will give an example of a set which is connected, but it is not path connected. Okay. So that's the next thing to do. Okay. This is still left. We will do this the next time. This is easy and formal. We'll do it. But this is the next goal, to show that connectedness is not. But again, just to repeat the point, in natural conditions, connectedness will imply path connectedness, and we will also explore that because that will also be needed. So this is the goal for now. Now, maybe it's a little hard for you to think an example. So maybe let's give a few ideas. So what does not being path connected mean? So we want an example. So we want a set S in R2 such that S is connected by the definition of open sets, the disjoint union of open sets, blah, 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 right? Such that S is connected, but not path connected. This is the type of example we need. Okay, so how, yeah. No, but concave sets, but give a concrete example, because if you just say concave sets, then I can say, look, this is a concave set. Is it connected? Yes. Is it path connected? Yes, because you can make a path between any 2 points. You can't make a line, but you can make a path. You can make a path. Right? I mean, even if it's a set like this, you're just touching at a point, you can still make a path. I mean, you understand, just go through this point somehow. Obviously, some conditions and weird things under which it will not happen, but we are working in the ordinary space, and so it should happen. So you can make a path. Now, this is obviously a continuous, you can write a continuous function whose image will be this. Now, obviously, you are right. There may be some concave sets for which this does not hold. But that's exactly the point. You have to give that example precisely, right? Otherwise, it doesn't pass. Okay. So it's going to be a very crazy set, maybe. I think so. I do not like the definition of concave is something which is not convex. So I think, yeah, if we go by that definition. Yes, I can't think of any other sensible definition. So yes. So you see, to give this example, we have to know more about connectivity. Okay. So let me talk about this thing, combining connected sets, combining two connected sets. Because unless we know more, it's difficult. Connected sets. Just 1 minute. Yeah. 1 second. I had something in mind which I am forgetting. Yeah. Okay. Yeah. Combining two connected sets. Let's explore this. So basically, we are trying to explore the calculus of connected, in the sense that if we take union, then what happens? If we take intersection, then basically these things will help you to create more examples, right? Create more non-trivial examples, and that's where you'll get your counter examples. Is that right? I mean, if I keep drawing different kinds of convex sets, then we are never going to learn anything new about connected sets, right? If I'm only going to draw pretty pictures, okay, not going to learn anything new. That's why we need to learn how to combine connected sets. We need to maybe able to take limit of connected sets and do different kinds of operations on connected sets and see what the results are. So there maybe we can find some. Okay. So this is the kind of example where you have a function which has the intermediate value property, but it is not continuous, and so we needed to do some things, right, to get such counter examples. It is so we need to just see how these things interact with each other. Combine into connected sets. Okay, so let S1 and S2, no, what am I doing? Let S1 and S2 be in R2, be connected. And this is also just a natural question to ask. It means it should be that the answer is yes, but is it yes? We'll see yes or no. We connected. So the question is then connected such that S1 intersection S2 is not empty. So they have a intersection, a set theoretic intersection. Okay, they have a set theoretic intersection. That's not needed. In fact, closure and such can be set. But 1 minute, can it be? No. That's okay. Anyways, let's see. Such that this is non-empty, which means that S is like this, and they are intersecting. To keep it simple for now, intersecting. Then is S1 union S2. I'm not asking about the intersection. Okay, let me first ask about the intersection. That's much easier. Is S1 intersection S2 connected? And second question is S1 union S2 connected? Let's think about these two things then. Okay, so but you have to prove it. Maybe so think about it more and try to prove it. So you can, by now, you should be able to give a proper proof. But also, if you just get the reasoning, think about it and tell me next time. But let's then think about this intersection. But this answer is correct. So that's why I'm not saying more now. But please think about this and try to formalize it. Let's think about the intersection then. Let's arrive at something, what it should be. So, Okay. Think. Okay, take your time and think. I will try to draw pictures and see. I'll just come in 2 minutes. Yeah. This will have a very straightforward explanation, whatever the answer is. So think about it. Okay, so what do you think now? Do you think it's connected? Okay. And but also intersection can be really small also. Okay. If I draw right, not connected. The intersection is just this block and this block. These two are far apart, right? They're not connected. And you can yeah. Okay, yes. Two intersections. Okay, but this is also an intersection. Okay, well, that's a good way to put it. Okay, right. But yeah, the answer to this you see is no. And you see this is very simple no. But yeah, you have to prove this. Okay, this answer is correct, but you have to prove it. Before ending, let me just give you one more problem which you should try. Okay, go back to the definitions and do it. Okay, if needed, you can see the definitions from here or the video. You can also see the definitions in the books, but sometimes they can be a little more abstract, but it depends. That's up to you. Okay? But here is the other question. So we asked about union and this thing. This is a more important question. This is a more, if S is connected, then is closure, this is called, I'll define this, though I've defined it already, but I'll define what it means here. Closure connected. Okay. Now, what does this mean? So this is called closure. This is called closure, but you know it in the other way I've said, but not this way maybe. Closure of S. What this is take S and take all the limit points also. of S. What do you mean by limit points here? Now, again, that is just saying that you take sequences in S and you take their limits. Sometimes they may be outside S and you need to take them. Okay, so this, as you know, but I'll just say it to be here. Limits of sequences. So you start with S and you take all the limits of the sequences in S, and the set you get is called the closure. Limits in S. So just take a very simple example. If you take the open circle, or the open disk rather, right? Then what will be the closure of it? The circle, the closed disk, right? With the boundary. Because those are the limit points, right? Because if you take some sequences like this, which are all inside in S, then the limit can be on the boundary like this. Okay, so it will be like this. Just take what word? No, that is connected. Why is it not connected? But I'm not, but see, I'm not drawing the circle. I'm drawing the open disk, but circle is also connected. If you take the, if you take the open disk and you take all the limit points, then you get the closed disk. Yeah. Obviously this is connected, but even if you just take the circle is obviously connected, right? It is the image of a function. I mean, e to the power I theta, right? That's obviously connected. You can go from any point to the other on the circle only. Okay, yeah, so the question is, if S is, this is the question, that if S is connected, then you take all the limit points, is that also connected? Yeah, so think about this. This is the delicate question. And then we can use these two. We'll do these two questions first next time, and then we will try to give the example. And also that continuous functions and connected relation. Okay. So yeah, okay, thank you. Thank you.